Okay, in this video, we're going to be talking about parent functions. Now, let's first off let's start out by describing what we mean by a parent function. A parent function is the simplest function of that type, I guess you could say. There's lots of different types of parent functions, and that's what we're going to be discussing in this. But these parent functions are parents of a family of graphs. And what we mean by a family of graphs displays similar characteristics. Like we know that all lines pretty much look the same. They might be slanted in different ways. They might cross the y-axis in different places, but they all have the same characteristics. They're all lines. And that's what we mean by these families of graphs. And the parent function would be the most basic types of those lines. A parent function is the simplest function of the family. So let's start out by looking at the parent function of a linear family. And that parent function would be y, or f of x, is equal to x. Now let's look at the graph of that parent function. Y equals x has a y-intercept of 0 and a slope of 1, and it looks something like this. 1, 1, 2, 2, 3, 3 are some of the points that are on this. The domain and range are both all real numbers because there's no breaks, there's no x values that are excluded from our domain. We can plug in anything and we can get anything when we plug those in. The x-intercept and the y-intercept are actually the exact same point, which is located right here. And that would be a 0, 0. Maximum number of roots and zeros. And again, what we mean by roots or zeros is where a graph crosses the x-axis. And there is only, if you have a line, there is only maximum, you can only have one intersection point. And now let's discuss the end behavior of this function. As we travel to the right on my graph, notice my graph goes uphill, so my y value approaches infinity. And as we travel to the left, we're going downhill. So as x approaches negative infinity, my y value approaches negative infinity as well. And this is a continuous graph. There are no breaks, there are no jumps, there is no discontinuity. Next up, our absolute value parent function, which is f of x equals absolute value of x, looks something like this. And notice it looks a lot like the previous graph. The only difference is when you plug in -1, you get +1. When you plug in -2, you get +2. It takes the absolute value of it. However, when you plug in 1, 2, and 3, you still get 1, 2, and 3. The domain here will be the same, because you can plug in any value that you'd like. However, the range, notice that there is absolutely no graph down here. So your range starts here with this y value of 0 and extends forever upwards. So that would be from 0 to infinity. Your x-intercept, you only have one, and it is going to be the exact same thing as your y-intercept, and both of those are located at 0, 0 again. The maximum number of roots or zeros of an absolute value function. And when we're talking about this, we mean of any absolute value function. If we were to transform this and bring it down and look something like this, sometimes we might have two zeros. So with this parent function, we only have one, but sometimes these might have two zeros. The end behaviors now. As we travel to the right on my graph, notice my graph goes up, and this parent function is what we're describing here. However, we know if we flip it over, it would have different end behaviors. As we travel to the left, notice we're also going uphill, so my y value always approaches positive infinity there, and that we are continuous everywhere on our domain. Quadratic, our most basic type, is y equals x squared. The graph looks like this, and it's called a parabola. The domain is, once again, there are no domain restrictions here, so your domain is once again negative positive infinity. Or we can say all real numbers. Our range, again, however, there is absolutely no graph below 0, so our range is now from 0 to infinity again. Once again, the x and y-intercept of this graph is the exact same point, 0, 0. And even though this graph only has one x-intercept, if you were to draw other parabolas, the maximum number of x-intercepts that you could have would be 2. Your end behavior, as you travel to the right on this graph, you're going uphill, and as you travel to the left, you're also going uphill. And this is continuous everywhere on its domain. Next up, you have your cubic function. And it looks a lot like your quadratic function of x squared. However, your cubic would be y equals x to the third. Here's what the graph looks like. And we were only really able to fit 3 points because it grows so quickly, because if you plug in 2, you get 8, which doesn't even fit on your graph. Your domain is once again infinite, all real numbers. And your range, because it does go up and down infinitely, would also be all real numbers. Your x-intercept and y-intercept are, again, the point 0, 0. And now let's talk about something interesting about the cubic functions. Now this is a parent function, however, different types of cubic functions might curve a little bit differently. And some of these cubic functions, let me change my color here, might look something like this, to where it doesn't just skim like this one does here, but it might go up, down, up, and it might have a little bit more hills and valleys. So some of these cubic functions could cross the x-axis up to 3 points. The same way a quadratic crosses up to 2 points, a cubic crosses up to 3, and later on we'll talk about x to the fourth and x to the fifth, which cross at possibly 4 times and 5 times. So next up, our end behavior as we travel to the right and left. As we go to the right, my graph goes up, and as we go to the left, my graph goes down. So let's go ahead and fill in those blanks. And finally, this is a continuous graph. There are no breaks anywhere on its domain. Next up, the square root function. Your most basic square root function will be y equals x, the square root of x. And its graph looks something like this, which is actually a sideways parabola, or actually half of a sideways parabola. Had we actually graphed plus and minus the square root of x, that would have also included the bottom, and it would be a complete parabola. Now, our domain here, we got to be a little bit careful now with our domain. We do have some restrictions. You cannot take the square root of a negative. We'll talk about a little bit more that the square roots of negatives will give you imaginary numbers. So therefore, our domain is only going to start at 0 and go to infinity. And notice that there is no graph below on your y-axis. There's no graph below 0 as well. So your range is also from 0 to infinity. Your x and y-intercept are still here at 0, 0, as with most of our graphs that we've talked about. And if you were to shift this graph around, move it, stretch it, skew it in all the different ways, it still would only cross the x-axis at 1 point. Your end behavior, as you travel to the right on this graph is continuously going up and up and up, so you are approaching infinity. There is no asymptote line. It does not level off at any certain point. It continues up forever. And we got to change our as we go to the left, because we can't approach negative infinity. So let's change that, because we don't go past 0. So instead of saying as x approaches negative infinity, we're going to say as x approaches 0, which is the first point on our graph. That's our first x value. And as we get closer and closer and closer to 0, my y value also gets closer and closer and closer to 0. Finally, is this a continuous graph? Now, I'm going to go a little bit away from, because there's different people say different things about this. I'm going to say that it is continuous. However, we've got to be careful, because it's continuous everywhere on its domain. Okay, is it continuous over here? No, because the graph doesn't exist over there. So on its domain from 0 to infinity, yes, this is a continuous graph. Okay, next up we have our cube root function, and here's the basic parent function of a cube root function. And we're going to notice the same way that x squared and x to the third, somewhat similar. Well, so is the square root of x and the cube root of x as we look at the graph here. So we notice that the same way that a square root function was like an x squared function sideways, and a cube root function is the same thing as an x to the third function kind of sideways. Your domain, however, notice that your graph goes forever left and right. So therefore, our domain is going to be from negative and positive infinity. And since we're growing to the right and shrinking to the left, going up forever and going down forever, our range will also be all real numbers. Our x and y intercepts are both going to be located here at 0, 0. And with this nature of what a cube root function looks like, it will always just cross the x-axis at one value. Our end behaviors as we approach positive and negative infinity. As we go to the right, my graph is going up to positive infinity. As I go to the left, my graph is decreasing towards negative infinity, and there are no breaks in this graph, so it is continuous. Next up, the reciprocal function. And your reciprocal function is the most basic of all the rational functions. It's y equals 1 over x. Here's what your graph looks like for your reciprocal functions parent. And this reciprocal function you can see here is going to have what's called asymptote lines. It kind of reminds me of the seams on like a baseball or basketball or something. It is called a hyperbola is the basic name for it. A lot like a parabola, but you got kind of a double looking parabola. Again, it's called a hyperbola. Your domain, you do have a domain restrictions. Notice that you have an x on the bottom of a fraction. X cannot be 0. So I'm just going to put for my domain, x is all values except for 0. You can write it like this, or you can write it like this, to where you include all values from negative to positive infinity except for, notice I do not include 0. Notice the range does the exact same thing. My graph kind of comes down towards 0 and stops. It kind of follows along with that x-axis, and the same thing here. Your graph never crosses the x-axis, so your range is going to be identical. It's going to be, and I'm going to put the other option, y is everything except for 0. Y can be anything else. Notice that you have graph everywhere else except for right here on the x-axis. X-intercepts and Y-intercepts, since you do not have an X-intercept, you don't have a Y-intercept, either one, we'll just put not applicable, or there's nothing there. Your maximum number of roots. If we were to shift this up or down, notice that we could have a root. Like if we did the 1 over x, we tacked on a +1 or something and moved it up, it would have a root there, but we would only have 1. Our end behavior as we go to positive infinity and negative infinity, as we go to the right, notice what happens to my graph. It levels off. We have this asymptote line, so my y value approaches 0. As I travel to the left, the same thing. It tapers. Okay, it gets closer and closer and closer to that exact same 0. This is a discontinuous graph, so therefore it does have an asymptote line. You have asymptote lines. You have a vertical asymptote line right here at x equals 0. And you also have a horizontal asymptote line that we get closer and closer to as we travel to the right and left of y equals 0. So you have two asymptote lines there. Next up, your exponential parent function. The most basic is going to be f of x equals 2 to the x. Now this is a little bit different because of that 2. You could also have a parent function of y equals 3 to the x or y equals 4 to the x. It all depends on what base that you are discussing in your problem. So let's take a look at what y equals 2 to the x power looks like graphically. Okay, domain-wise, you can plug anything in that you would like into this graph. Your graph goes forever to the left, and it also goes to the right forever. Your range, however, notice that there is absolutely no graph down here, and we also have another asymptote line. This thing gets closer and closer and closer to your x-axis, but it never touches it. So therefore, we're going to say my range starts at 0, but does not include it, and it goes up from there. Your y-intercept and your x-intercept. Okay, we just said that it never crosses the x-axis, so therefore it will not have a y-intercept. You can put either not applicable or no solution. Excuse me, that's your x-intercept, not applicable. And then your y-intercept, it does have a y-intercept right here of 0, 1. Maximum numbers of roots or zeros. If you shifted this around up or down, it could have a root if it got moved down a little bit. And then finally, your end behavior as you go to the right and to the left. As you travel to the right, your graph goes up forever. As you travel to the left, it does not go down forever. It tapers. Okay, it gets closer. It levels off, and it levels off at y equals 0. It is a continuous graph. However, it does have an asymptote line, and we've already discussed this. This is the line that as we travel to the left, we get closer and closer and closer to. That would be the line y equals 0. And then finally, our logarithmic parent function. And we'll say y equals log of x. Now, this would be a common log, so this number down here could be, again, the same as the previous one, y equals 2 to the x. This could be log base 10 of x as it is here. We could have a log base 2 of x, log base 3 of x. We could have several parent functions here, all depending on what our base is. However, we're going to look at just y equals log base 10 of x. Here's the graph of it. And notice this looks a lot like your exponential function. It's because they are inverses of each other. Your domain, now you do have a domain restrictions. There's nothing over here. Plus, notice that your graph gets closer and closer and closer to the y-axis here. So therefore, your domain does not include zero, and it only includes positive values. And the way we remember that, you cannot take the log of a zero, you cannot take the log of a negative. So it only includes zeros to infinity. Your range, however, you go down forever, and it tapers up very slowly, but it also goes up forever. So that'd be negative to positive infinity. Your x-intercept is where it crosses the x-axis, which is right here at 1, 0. However, since we have that asymptote line, it does not cross the y-axis, so there's no y-intercept. Maximum numbers of roots and zeros, no matter how you skew it, you're only going to have one. And then finally, my end behavior, as we approach positive infinity, or as we go to the right, my graph is going uphill very slowly, but it is traveling uphill. And as x approaches, we can't approach negative infinity because there's no graph over here. So we're going to approach the smallest value on our graph, and that's going to be, we're getting close to zero. We know we can't touch zero, but we can get close to it. But as we travel to the left on my graph towards zero, my graph shoots downhill to negative infinity. Continuity, we are going to say the same as a square root function. I can draw this without lifting my pencil, so it's continuous everywhere on its domain. It is not continuous over here, obviously, because there's no graph, but everywhere on its domain, it is continuous. It does have an asymptote line because it gets closer and closer and closer to this vertical line, which is at x equals 0. It never crosses it, so we do have an asymptote line there.